Hello, this is video number 16 on my single variable calculus 2. In this video, we're going to go over partial fraction decomposition. We are going to evaluate the integrals of rational functions. Rational functions are ratios of two polynomials. I'm going to show you how we can evaluate these integrals with a few examples, and then at the end, I'll summarize the entire process. The first example is evaluating the integral of x to the power of 4 plus 2x over x minus 1, and this is an indefinite integral. So whenever the degree of the numerator is larger than or equal to the degree of the denominator, we perform long division. So let's perform long division, and then from there we would be able to evaluate the integral. So we're going to take x to the fourth plus 2x, and we are going to divide that by x minus 1. So we are going to divide the leading terms, x to the fourth over x, that gives you x cubed. Multiply it out, we get x to the fourth minus x cubed. We are going to subtract, this becomes minus, this becomes plus. We are going to get x cubed plus 2x. Divide x cubed by x, we get x squared. Multiply it through, we get x cubed minus x squared. Change the signs again here. We are going to subtract and get x squared plus 2x. Divide x squared by x, we get x. Multiply it out, we get x squared minus x. Subtract, we get minus here plus here. And that gives us plus 3x. Divide 3x by x, we get 3. Multiply it out, we get 3x minus 3. Subtract, and we are going to get 3 as the remainder. So the remainder is 3, and the quotient is x cubed plus x squared plus x plus 3. That means the integral that they gave us is the same as integral of x cubed plus x squared plus x plus 3 plus the ratio of 3, which is the remainder, over x minus 1 dx. So how do we integrate this? Well, the first portion is a polynomial, so that's x to the fourth over 4 plus x cubed over 3 plus x squared over 2 plus 3x. The last portion is a natural log, so it's 3 natural log of x minus 1 plus c. Now, if you don't see how the integral of the last one is done, the integral of 3 over x minus 1 dx can be done by a u sub. You can do u equals x minus 1, so du is going to be dx. If the denominator were, say 2x minus 1, then your du would be 2 dx. So it wouldn't be natural log of 2x minus 1. So this would be integral of 3 over u du, which is 3 natural log of absolute value of u plus c. So that's another way of doing the final integral. So let's look at the next example. The next example is the integral of 4 over x squared minus 1. The main idea here is after performing long division, we are going to break down the integrand into simpler pieces. First of all, the numerator has degree 0 because this is a constant, and the denominator has degree 2. So no long division is needed. We are going to take 4 over x squared minus 1, and we are going to break this up into x minus 1, x plus 1. So that gives us two pieces. One of them is with the denominator x minus 1. The other one is with the denominator x plus 1. So we are hoping to write down this fraction into two smaller fractions, simpler fractions, that we can evaluate their integrals. So we are going to clear the denominator. So clearing the denominator gives us, we're going to multiply by x minus 1 times x plus 1. So on the left we get 4, on the right we get a times x plus 1 plus b times x minus 1, because when you multiply by this, x minus 1 cancels here and x plus 1 cancels over there. Now there are two different, and this should be x minus 1, there are two different ways of evaluating x, a and b. Method number 1 is going to be by substituting values of x. So if we plug in x equals -1, the coefficient of a disappears. So we get 4 equals a times negative 1 plus 1 plus b times negative 1 minus 1. This is 0, so the other one gives us b equals negative 2. If we plug in x equals 1, the coefficient of b disappears. That would be a times 1 plus 1 plus b times 1 minus 1. And that gives us a equals 2 because it is 4 equals 2a. So that means the integral was separated into two simpler integral. Method number 2 for finding these two coefficients a and b is to write down this expression by combining like terms. So bx minus b. Now the terms with x are the ones with ax and bx, so that would be a plus b times x. And the constant term is a minus b. Now this 4 must be equal to that. Now we're going to set the coefficients on the two sides equal. Coefficient of x on the left side is 0 because there is no x on the left side. Coefficient of x on the right side is a plus b. Constant term on the left side is 4. Constant term on the right side is a minus b. We are going to solve this one for b. B is negative a. Plug it into the bottom one. We get 4 equals a minus negative a. So this gives us a equals 2 and b would be negative a, which is negative 2. So that obviously gives us the same answers as we got before. Now you could use either of these two methods, but sometimes method number 1 doesn't quite work when we get to later types of examples. So now we are going to substitute into our expression. So the integrand was this. So this is equal to a, which is 2. And then we have b, which is negative 2. So, well, let's see what the denominators were. The first one is x minus 1. The second one is x plus 1 dx. Now the first one is 2, and then again using a similar technique is natural log of x minus 1, and the other one is natural log of x plus 1, and of course plus c. So that is the answer to the integral that they gave us. Okay, let's look at the next example. The next example is again an example that the numerator has a degree less than the denominator, so no long division is needed. Your first step would have to always be to perform long division if necessary. Next is to take the denominator and factor the denominator. X cubed plus x squared minus x minus 1 can be factored by grouping. So we're going to group these into two groups of 2. We get x squared times x plus 1. We are going to factor a negative sign from the second term, from the second group. So we get x plus 1 times x squared minus 1. We need to factor this completely, so we get x plus 1 times x minus 1, which is x plus 1 squared times x minus 1. Now we're going to write down the partial fraction decomposition. So this is 2x plus 1. We have x plus 1 squared times x minus 1. So this would be, because the degree of the denominator is 3, we will have 3 fractions. And here is the setup for the fraction. For each of these terms, we'll have one term. So, well, we have 2x plus 1s, so we have 2 terms. One of them is x plus 1, one of them is with x plus 1 squared. And then we have one x minus 1, so we have an x minus 1 as one of the other terms. So this would be a, b, and c. Now we are going to clear the denominator. So if we multiply by x plus 1 squared times x minus 1, we get 2x plus 1 on the left. We get a times x plus 1 times x minus 1 plus b times x minus 1 plus c times x plus 1 squared. Now we could use either of the methods that we learned before to find ABC. I'm going to use the first method. So if we plug in x equals 1 to get 3 on the left, on the right we get a times 2 times 0 plus b times 0 plus c times 2 squared. So that gives us c equals 3/4. Next we plug in x equals negative 1. We get negative 1 on the left, 2 times negative 1 plus 1, a times negative 1 plus 1, negative 1 minus 1 plus b times negative 1 minus 1 plus c times negative 1 plus 1 squared. So the a term, this is 0. This is also going to be 0. So we get b is equal to 1/2. So from here we got b and c. Now you can plug in basically any x that you want. So let's plug in x equals 0. That's probably the simplest one after 1 and negative 1. So that on the left we get 1, on the right we get a times 1 times negative 1 plus b times negative 1 plus c times 1 squared. We are going to plug in the values of b and c. We get 1 equals negative a minus b, which is minus 1/2, plus c, which is 3/4, which is negative a plus 1/4. So that tells us 3/4 is equal to negative a. So a is equal to negative 3/4. So this means the integral that they gave us is the same as negative 3/4 over x plus 1. I believe that was the first fraction. Then we had b, which is 1/2 over x plus 1 squared. And then we finally have c, which is 3/4 over x minus 1 dx. Next, we're going to evaluate these integrals. That's negative 3/4 integral of 1 over x plus 1, which is natural log of x plus 1. Then we have 1/2 integral of 1 over x plus 1 squared dx. And then the last one is 3/4 natural log of x minus 1. Now for the middle one, you can either use power rule or you can use a u substitution. So either way, we're going to get negative 3/4 natural log of x plus 1 plus 1/2. So we can use power rule because derivative of x plus 1 is just 1. So this would be x plus 1 to the power of negative 1 over negative 1 plus 3/4 natural log of x minus 1 and then plus c. To simplify this, we are going to get, I'm going to put the positives at the beginning, 3/4 natural log of x minus 1 minus 3/4 natural log of x plus 1 minus 1 over 2 times x plus 1 and then finally plus c. So that would be the answer to the problem. Next example. If we look at the next example, again, we don't need to do any long division because the numerator has a smaller degree compared to the denominator. So we'll have to factor the denominator. So we have x cubed plus x. We can factor it as x times x squared plus 1. This is the best we can do when we factor this one because x squared plus 1 cannot be factored into linear factors because its roots are not real. So what we do is we're going to write down the partial fraction decomposition in this form. So we have one term that is x and then only one term that is x squared plus 1. So this would be a, but for the quadratic term, it would be bx plus c because I need two variables, two unknowns for the quadratic. And look at the previous one, we also did basically the same thing. For the quadratic term, we had two unknowns of a and b. So after we clear the denominators, which is going to be a very similar process to what we did before, we get 2x minus 1 on the left. We get a times x squared plus 1 plus b x squared plus cx. Now we can use either of those two methods to find ABC, but it's probably better to compare the coefficients. So we have 2x minus 1 equals ax squared plus a plus bx squared plus cx. So this side is a plus b times x squared plus cx plus a. I'm rearranging these to write down the right hand side in order of the degree. Now we are going to compare the coefficients. We have the coefficient of x squared is 0 on the left. Coefficient of x squared is a plus b on the right. Coefficient of x is 2 on the left. Coefficient of x is c on the right. The constant term is negative 1 on the left and it is a on the right. So we can plug it in here. We get 0 equals negative 1 plus b, which means b is equal to positive 1. So that tells me that integral of 2x minus 1 over x cubed plus x dx can be written as -1 over x, and the other as b, which is x, plus c, which is 2 over x squared plus 1 dx. So this is the integral that I need to evaluate. How do I evaluate this one? Well, the first term is minus natural log of x. For the next term, we'll have to break this up into two different integrals, and I'll do that in the next step. So this is minus natural log of x plus integral x over x squared plus 1 dx plus integral of 2 over x squared plus 1 dx. For this term, we'll have to use a u substitution. U equals x squared plus 1. Du would be 2x dx. We are going to substitute x dx by 1/2 du. We get minus natural log of absolute value of x plus integral 1/2 du over u plus 2 tan inverse of x. That is just directly from the table. And that is equal to minus natural log of absolute value of x plus 1/2 natural log of absolute value of u plus 2 tan inverse of x plus c. And of course, we'll have to write down the final answer in terms of x only. So this would be minus natural log of absolute value of x plus 1/2 natural log of x squared plus 1 is what u was, and x squared plus 1 is positive, so I don't need the absolute value, plus 2 tan inverse of x plus c. And that would be the final answer to this problem. Okay, let's look at a couple more examples. The next example is evaluating this definite integral. So if you notice, there is one term of cosine here. If you factor cosine, there's one cosine here, and everything else is in terms of sine. So it makes sense to do a u substitution for sine because its derivative is right there. So we'll do u equals sine of x. So that gives us du equals cosine of x dx. Now, when x is 0, u is 0 also. When x is pi over 2, u is 1. So we can use that and turn this into integral from 0 to 1. Now, cosine of x dx, so we can write this down as 0 to pi over 2. We can write it as 1 plus sine squared of x. Then we have cosine of x, and then dx. And then the same denominator, sine cubed plus 3 sine squared plus 4 sine plus 2. Now, how do we integrate this? Well, we do the u substitution that we just did, and it turns it into a rational function. So sine x, cosine x dx is du. So we have du here. And then the numerator is 1 plus u squared. The denominator is u cubed plus 3u squared plus 4u plus 2. And we will have to factor this one. We have to factor the denominator. Notice that the numerator has a degree that is less than the denominator, so we don't need to do any long division. So we'll have to factor the denominator. Now, this is not an obvious factorization that we can do, but we can find a root of the denominator. So a root can be found as, and you can just test this one. If you plug in any positive number, you're just going to get a positive number. If you plug in, let's say u equals -1, we are going to get -1 plus 3 minus 4 plus 2, which is in fact 0. So this is in fact a root of the denominator. So we have a factor of u plus 1. So thus, u plus 1 is a factor. So if u plus 1 is a factor, we can find the other factor by doing long division. So we take the denominator, which is u cubed plus 3u squared plus 4u plus 2, divide by u plus 1. So if you divide u cubed by u, you get u squared. So we get u cubed plus u squared. We are going to subtract to get 2u squared plus 4u plus 2. divide 2u squared by u, we get plus 2u, 2u squared plus 2u, subtract, and we get 2u plus 2, divide, and we get plus 2, multiply, we get 2u plus 2, and of course the remainder is 0. So that tells us that the denominator, which was u cubed plus 3u squared plus 4u plus 2 can be factored as u plus 1 times what we found as the quotient, which is u squared plus 2u plus 2. Now, of course, this term does not have any real roots because its discriminant is going to be b squared minus 4ac, which is negative. So this has no real roots. So because it has no real roots, we cannot factor this one any further, which means this would be as much as we can do. So we can start with 1 plus u squared over u cubed plus 3u squared plus 4u plus 2. We wrote it down as 1 plus u squared over u plus 1 times u squared plus 2u plus 2. So now we can use the partial fraction decomposition. Now the denominator, it has two pieces. One of them is u plus 1 and the other one is u squared plus 2u plus 2. So we can write this as bu plus c. Now let's clear the denominator. We get 1 plus u squared is equal to a times u squared plus 2u plus 2 plus bu plus c times u plus 1. Now we'll have to find the constants a, b, c, and then use the techniques that we have learned before to evaluate this integral. Let's evaluate the coefficients by multiplying this out and setting the coefficients equal. So 1 plus u squared is equal to au squared plus 2au plus 2a plus bu squared plus bu plus cu plus c. So if we combine like terms, we get a plus b times u squared plus 2a plus b plus c times u plus 2a plus c. Now, what is the coefficient of u squared? That is 1 on the left. It's a plus b on the right. What is the coefficient of u on the left? That is 0. What is the coefficient of u on the right? It's 2a plus b plus c. What is the constant term on the right? It is 1, or rather on the left. On the right, it is 2a plus c. So we can find ABC from here. We can take the last two, subtract them. You get b is equal to negative 1. You can plug it into the first one. We get a is equal to 2. And finally, we can plug it in the last one. We get 1 equals 4 plus c. So c is in fact negative 3. So this means the integral that we had, or rather the integrand that we had, which was 1 plus u squared over u plus 1 times u squared plus 2u plus 2, can be written as a, which is 2, over u plus 1 plus u squared plus 2u plus 2 is at the bottom, b u plus c over the quadratic. So this is the integrand. So we can integrate this. So integral of 2 over u plus 1 from 0 to 1, I believe, is what we started with. Yes, from 0 to 1. And then plus integral from 0 to 1 of minus u minus 3 divided by this quadratic. Now, notice that this quadratic doesn't have any roots, so we'll have to complete this square. So we get u plus 1 squared plus 1. And this would be one of the tangent inverses, or perhaps a natural log. So this is equal to, the first one is 2 natural log of absolute value of u plus 1 from 0 to 1. For the second one, we'll have to do a substitution for u plus 1. So we get t equals u plus 1. dt becomes du. u is t minus 1. When u is 0, t is going to be 1. When u is 1, t is going to be 2. So this is the integral from 1 to 2 minus t plus 1 minus 3 over t squared plus 1 dt. So the first one is 2 natural log of 2 minus 2 natural log of 1. So that's what we get for the first term. Then we get minus integral from 1 to 2 of t over t squared plus 1 dt. And then minus 2 integral, because this is going to be negative 2, integral of 1 over t squared plus 1 dt from 1 to 2. Okay, so the middle one, this one, can be evaluated by another substitution for t squared plus 1. So this gives us dz equals 2t dt. And the limits are going to be if t is 1, z is 2. If t is 2, z is 5. So we are going to get 2 natural log of 2. Natural log of 1 is 0, so we can ignore that one. And then we get minus, well, t dt is 1/2 dz, integral from 1 to 2 of dz over t squared plus 1, which is z. Now, the limits of z are going to change from 1 to 2 to 2 to 5. And then minus 2 tan inverse of t from 1 to 2. Let's now substitute, integrate, and substitute. So we get 2 natural log of 2 minus 1/2 natural log of z from 2 to 5. And then the last one is minus 2 tan inverse of 2 plus 2 tan inverse of 1. So this would be 2 natural log of 2 minus 1/2 natural log of 5 plus 1/2 natural log of 2 minus 2 tan inverse of 2 plus 2 times pi over 4, which is tan inverse of 1. So let's simplify this and see what we get as the final answer. Well, this one is pi over 2. I'll just put it at the beginning. Then I have 5/2 natural log of 2. Then I have minus 1/2 natural log of 5. And then eventually I have 2 natural log of 2. So this will be the answer to this problem. Let's look at one more example. So I have 2 more examples and then I'll summarize. Okay, so for this example, we'll have to use integration by parts first. So we'll do u equals natural log of x squared plus 1, and dv would be dx, and there's a dx here that is missing. So that gives us du equals derivative of natural log, which is 1 over x squared plus 1, times the derivative of inside dx, and v would be x. So we get the integral from 0 to 1 of natural log of x squared plus 1 dx is equal to uv, which is x natural log of x squared plus 1 from 0 to 1 minus integral of v du, which is x times 2x over x squared plus 1 dx from 0 to 1. Let's plug in the values. We get 1 times natural log of 2 minus 0 minus integral of 2x squared over x squared plus 1 from 0 to 1. So now we see that the denominator has degree equal to the numerator, so we'll have to do long division. So we get 2x squared divided by x squared plus 1. The ratio is 2. Multiply, we get 2x squared plus 2. Subtract, we get negative 2. So this is natural log of 2 minus the integral from 0 to 1. Quotient, which is 2, minus 2 over x squared plus 1 dx. Now this gives us natural log of 2 minus, well, integral of 2 is 2x, and integral of 1 over x squared plus 1 is tan inverse of x. And this would have to be evaluated from 0 to 1, but only this portion. So that would give us natural log of 2 minus, by the way, this is still a minus sign. We are going to plug in 1. We get 2 minus 2 tan inverse of 1. We're going to plug in 0. We get 0 and 0. So this would be natural log of 2 minus 2 minus tangent inverse of 1 is pi over 4. So that would be minus pi over 2. And this would be the final answer to this problem. Or rather, plus pi over 2, because there's two negative signs here. Okay, and this is the last problem. So evaluate this integral. So now, if you look at this one, first of all, we don't need to do any long division because the numerator has degree 1, the denominator has degree 4. We also can't really do any partial fraction because it is of the form quadratic at the bottom and then the numerator is ax plus b. We can't really factor the denominator any further. So this is already, the partial fraction has already been done. So how do we deal with that? Well, we'll have to take x and do one of those the trigonometric substitutions. Because of x squared plus 1, it makes sense to use x equals tan of theta. Now, if x is 0, that tells us that tan of theta is 0. And remember that whenever we did the tangent substitution, theta was between pi over 2, negative pi over 2 and pi over 2. So this would give us theta equals 0. When x is 1, then tan of theta is equal to 1, which gives us theta equals pi over 4. So then we can do the d theta. D theta is secant squared theta. Or rather dx is secant squared theta d theta. So the integral that they gave us turns into integral, instead of from 0 to 1, we will have to do from 0 to pi over 4. Instead of 2x plus 2, we have 2 tan of theta plus 2 divided by x squared plus 1, which is tan squared of theta plus 1 squared, and then dx, which is secant squared of theta d theta. So next, we are going to simplify the integrand. So we have 2 tan of theta plus 2. The denominator is tan squared theta plus 1, that is secant squared. So that's secant squared of theta squared, and then we have secant squared of theta d theta. So here we have secant squared, that cancels with one of the secant squareds here. So this would be the integral from 0 to pi over 4, 2 tan of theta plus 2. We have 1 over secant squared, that is cosine squared. We are going to distribute to see what we get. So we get integral from 0 to pi over 4. We get 2 tangent is sine of theta over cosine of theta. When you multiply by cosine squared of theta, one of the cosines cancels. So we get this expression. So one of the cosines cancels, and we get integral from 0 to pi over 4. And then we have 2 sine of theta cosine of theta, and then plus integral plus I forgot d theta plus integral from 0 to pi over 4 2 sine squared of theta. How do we integrate 2 sine squared? We have to use double angle formula, which is 1 plus cosine of 2 theta d theta. Now, for the first one, we'll have to use u substitution for either sine or cosine. We could use u equals sine of theta. That would tell us du equals cosine of theta d theta. So this gives us integral. When theta is 0, u is 0. When theta is pi over 4, u is root 2 over 2. And then we get u du. Or rather 2u du, plus integral of 1 is theta, integral of cosine is sine, and then we have to divide by 2 because of the chain rule from 0 to pi over 4. Next, we're going to have to integrate the first one, which is u squared from 0 to root 2 over 2 plus pi over 4 plus 1/2. And when you plug in 0, you get 0. So this gives us root 2 over 2 squared, that's 1/2, minus 0 plus pi over 4 plus 1/2. Simplifying that, we get 1 plus pi over 4 as the final answer. To summarize, anytime you want to evaluate integrals of rational functions, you will start with performing long division so that the numerator has a degree that is less than the denominator. After you perform that long division, then you completely factor the denominator. So you have to make sure that the denominator is completely factored. The terms would have to be either linear terms or quadratics with no real roots. Next, we'll perform the partial fraction decomposition. For every factor of ax plus b to the power of n, you use a term a over ax plus b to the power of k, and k ranges from 1 through n. So if you have ax plus b cubed, then you have 3 terms: ax plus b squared, ax plus b cubed. For each of the terms of the form ax squared plus bx plus c to the power of n, you use a similar term, but except that in the numerator you would have ax plus b. And in the denominator you have the quadratic to the power of k. K ranges from 1 through n, similar to the previous case. Then you clear the denominator, you solve for all of those variables, a, b, c, etc. And then after you find those variables, then you integrate a over x plus b to the power of k by a u substitution for ax plus b, and you integrate the other ones, the quadratic ones, by completing the square. And that sometimes, if k is greater than or equal to 2, requires you to use integration by substitution, trigonometric substitution of tangent of theta. And that brings me to the end of this video. I will see you in the next video.